So in this video, we're going to talk about differentials, and for the first time in ever probably in this class, we're going to look at this dy dx a little differently, okay? And so to get this started, I'm going to start you with an interesting picture that will hopefully clarify a lot of what we're talking about. This piggybacks on the idea of our linearization, where we study the equation of a tangent line and how it's not an exact replication, but instead it's an approximation of a value. So if this is our function y equals f of x, and this is our tangent line right here, and there's our point of tangency. Now I'm going to go ahead and drop down a line here. I'm going to pick another point on my graph, and I'm going to come down here. And at the same time, I'm going to focus on this guy right here, over and up. See how that's made a triangle there, a right triangle nonetheless. And so that right triangle, we can label parts of it. We know the slope of this tangent line is our dy dx, right? Well, that's just the change of y over the change of x. So independently now, for the first time, we're viewing this as a dy and this as a dx, okay? So we're treating the dy and dx not as one collective notation anymore, but now independent of each other. And so what I want to point out is the big key difference here. There's two things we need to look at. The first one is the horizontal distance between these 2 points, okay? The horizontal distance between these 2 points is right here. The vertical distance between these 2 points is here up to here, all right? Now, you can see my dy is not truly the change from here up to here. That dy is an approximation. The actual change we would want is this right here, right? That's the actual vertical change. And so we're going to call that red thing delta y. So there is a difference between dy and delta y. There's a difference between the vertical change and the approximation using the line versus the actual change between the 2 points. So dy and delta y are not the same, but they're approximate. Dx, however, there's no way around it. The horizontal distance between those 2 points, regardless of if it's an exact approximation or not, is actually going to be equal to delta x. Okay, so there's no difference in dx and delta x, but there is in dy and delta y. So having labeled it as we have, then I'm going to call this guy right here, I'll call this guy x. If that's x, then this would be x plus delta x. Our y-coordinate here would be f of x, and our y-coordinate here would be f of x plus delta x. All right, now let's make some observations and kind of summarize this. So observe. We know that delta x is equal to dx. That's one of the things that we observed. We also observed that delta y is approximately equal to dy. Not the same, but close. So what is delta y exactly equal to? Well, delta y was defined as the true vertical distance between the 2 points, this guy up to this guy. So how far is it from there to there? Well, it's going to be f of x plus delta x minus f of x. And then what is dy? Well, for dy, we're going to have to be a little bit clever. We know that dy dx together is the same thing as f prime of x. But if I now treat it independent, the dy and the dx independent of each other, I can multiply this dx to the other side, and I can say that dy equals f prime of x dx. And so this quantity right here, this represents what's called the differential. We'll study differentials a lot throughout this course, in particular when we get into integral calculus in the second half. But these are some really necessary observations to make here. From our picture, dx and delta x are the same. Delta y and dy are approximate. That's where this whole approximation idea comes into play, that this distance from here to here is not the true distance from here to here. And then we've identified exactly what delta y and dy are precisely. All right, so this problem is on page 42, or not page 42, it's number 42 on page 172, excuse me. And I've got the essence of the problem up on the screen. You're given a diameter of a tree at 10 inches, then over the next year the circumference increased 2 inches. And then how much did the tree's diameter increase overall? Now, the problem, the difficulty in this problem isn't so much going to be doing it, but it's going to be understanding which is the most efficient way to go. There's also a part B to this problem, and so I'm going to give you a little bit of guidance as to why I'm doing certain things a certain way due to part B. Now, again, you're given some things that are a little bit cross-balanced. You're dealing with a diameter, you're dealing with circumference as well. But then in part B, we're going to also be needing to talk about a radius to a certain extent. So I'm going to do this problem one way, and I'm going to tell you another way to do it that is even easier. I'll leave that up to you, but the way that I'm doing it is because I know what's coming in part B, okay? So in a problem like this, we're going to go ahead and we're going to start with this idea of circumference. Circumference is 2 pi r. And you're probably thinking to yourself at this point, well, yes, it is, but circumference is also pi times the diameter. And it is, you're right. This way over here to the right of that line, that's going to be the easy way to solve part A that I'm going to leave up to you guys. I'm going to solve it a little more in a difficult fashion so that I can use this result as well into part B. Okay, so we'll take this thing here, and I'm actually going to go on both sides of it and dr. In doing this, this is going to give me dcdr equals 2 pi. And learning and using what we've learned about differentials, I'm going to move the dr to the other side so that dc now equals 2 pi dr. And I'm interested in now knowing how much did the tree's diameter increase. Well, if I solve for dr, that's going to give me a dc over 2 pi, and the change of the circumference has increased by 2 inches. So the change of the circumference is now going to be 2, and we've got our 2 pi on bottom, leaving us with a 1 over pi. So that's the change of the radius. Therefore, for the diameter, that's going to need to be doubled for 2 over pi. Okay, so that's what we're looking for in part A. The change of the tree's diameter is going to be 2 over pi, and I'm guessing it's inches. Now, you could have done the same thing over here with C equals pi d if you d it. Now that sounds kind of silly, but this d right here refers to this guy. So if you do the same thing essentially I did here, but now with respect to d in this formula, you'll end up with that same 2 over pi. And so I would encourage you to finish that problem out. Now you won't have to double it like we did, but you'll still get that same exact answer. So I'm going to go ahead and clear the screen now and look at part B, and this will shed a little light onto why I did part A the certain way that I did. So part B of this problem now uses the same given information, but they're asking how much did the cross-sectional area increase? So for cross-sectional area now, we're going to need A equals pi r squared, right? The area of a circle, a circular tree. And that's why, again, I used that formula in the first part, dealing with the radius, knowing that we were coming with this. Had you worked it the second way that I showed you, you would have had a result of diameter, in which case you would then have to adjust that in this step. So bottom line is, pick one, it doesn't matter. You can get the same answer both ways, but you'll have to adjust either the first part or the second part accordingly. All right, so I'll take this thing now, and I'll do pretty much the same thing I did last time. I'll DDR both sides, which gives me my change of area with respect to the radius, and that's going to be a 2 pi r, and moving the dr to the other side, I've now got an opportunity to solve for that change of area that I've been looking for, right? How much did the cross-sectional area increase? So dA is going to equal 2 pi. The radius is going to be 5. I know the radius is going to be 5 because the diameter started with was 10. So half of that. And then our dr, that's that value we found in the last step, or in the last problem, that was that 1 over pi. So the dA is going to be your 10, and in this case, inches squared, since it's an area calculation. So once again, taking advantage of the differential and being able to separate the dr and moving it over, that's that same dr we had before. And like I said, I've said it a couple times now, I don't want to force you into working a problem a certain way. If you chose to go the circumference equals pi d in that first part, and you want to make the adjustments in the second part, feel free, you'll get the same answer. But this is the way that I chose so that I could take advantage of what I used in that first part already. So again, some interesting applications. Again, differentials will come up as well later in the course in a different context. Right now, the big part is starting to understand the notation and how it ties in to this whole idea of change, increase, decrease, those types of things.